A, B, C, D, E. That's pretty much it. By the time we're done here, we will explore the original 5 classes of IPv4 addresses. And when I say the original 5, that's pretty much the only 5 classes of IPv4 addresses. And first thing that immediately springs to mind is I keep saying IPv4 instead of IP addresses. It's almost a twitch I've developed nowadays because here we are, 2020, we're moving into an era of IPv6, which is slowly taking over the world. And when I say slowly, I remember when I first started teaching, and I was teaching Internet Information Service, had to be around the year 2000, IIS-3 for Microsoft, and I said, I have a prediction by 2003, Internet version, IP version 6 will take over the world, and I was obviously gravely mistaken. So this is not a new protocol, but it's now something that is becoming a big reality. So that's the first thing that comes to mind, and more on that a little bit later. Second thing that comes to mind is as we look at the original 5 classes of IPv4 addresses, we're going back in time, 1960s, 1970s, when this was all being developed, but that time is still now. We're still using those same classes of addresses as I'm starting to talk about what's known as class full addressing. And again, before we do, I want to remind you of the why, is because early on when I was building this network diagram, I just used temporary IP addresses like 192.168.1 to address the network, and that doesn't scale. This is a group of addresses that is intended for home network environments. And when I say intended for, an IP address is an IP address. You can use them for whatever it is you want, but the size of that only goes up to 254 usable addresses. This goes to 255. You can't use 0. You can't use 255. So 1 through 254 is actually usable addresses on this network. And in our networks of today, that doesn't scale. So let's look back at the original designers to see what they would say. Because when IP addressing was being developed, there are 3 primary classes of addresses that was designated for use in our networks of today: Class A, Class B, and Class C. Class D was designated for multicast use. So instead of thinking of those as IP addresses, like, hey, I'm going to speak from my computer to that server right there, and each one of them has an IP address that it's using to communicate, a multicast is kind of like a radio station where you have a whole bunch of computers that are like zombies, all tuned in to a certain frequency. So if you wanted to do that, you would give them all the same multicast address, 224, let's just say, .0.0.50 or something like that. And they would all be assigned that same address, and it's like they're listening to that same frequency. That's what multicast is all about. And Class E was designated and set aside for experimental use. What that is, only NASA knows. But I'm sure it has things to do with embedding IP addresses in mice and things like that. Regardless, this is the addresses that we use in our networks of today. Now you might be looking at them and going, okay, well, I see numbers. What does the numbers mean to me? This represents the number that you see as the first octet or in the first octet of the IP address. So if I looked at an IP address, let's just grab one, 10.50.1.1. I would look at that and go, okay, 10, Class A address. Okay, how about 11. Stop, Class A address. How about 12. Stop, Class A address, right? I look at that first number and I immediately know what class of address it is. So, 172. Stop, Class B address. Right? It's that easy. So just look at that first number and you immediately know what class of address it is. Okay, useful, but not, because I don't know what that means. The class of address dictates what original subnet mask was given to that group of IP addresses. Meaning, if the address started with the number 10, it was originally part of Class A, which had the subnet mask 255.0.0.0. If it had 172, it would be part of Class B, which had the subnet mask 255.255, excuse my penmanship there, .0.0. If it was, let's just say 192.168.1, it would be 255.255. It's again, it's like 1, 2, 3, this easy. The subnet mask, by default, for each of these classes of addresses just kind of grows as it goes down. Now, knowing what we know of subnet mask, what's that mean? It means that the higher classes of addresses have larger networks that they could have. And I'm talking in the original, these are all known as the class-full addresses. And in the class-full networking world, we went from really big networks to really moderate-sized networks. Like, take a look at this one. If I had, let's just say, the IP address 10.1.50.1, and it had the normal class-full subnet mask, that would mean there's one network. It's the 10 network, right? If I'm a computer on that network, I have that address. Like, I go, I am a member of the 10 network, and I can reach anything else that starts with the number 10 because that's all on the same network. That's all on the same switch. That's all in the same world. I don't have to go through a router to reach that. But what does that give us? Well, if you took every one of these values, and remember, they all go from 0 to 255, right, for each one of these, that gives us a network that has 16,777,214 computers on it. And I say computers, but I really mean devices. Now, that's insane. Like you can't have a network with 16 million devices on it because the ARP traffic alone would cause it to blow up. There'd be so much traffic, so much broadcast, so much chatter going around the network. The processor of the devices would have to just spin just to try and keep up with all the broadcasts and messages that are going around. So obviously, even though it can scale to that size of network, it wasn't intended that we would use that size of networks. And I have been in networks, by the way, where people just use the default class-full subnet mask of, let's just use 255.0.0.0 because I don't know what I'm doing, or I don't care what I'm doing. And they would throw that out there, which pretty much means you could have a network that could have 16 million addresses on it. But I would say the travesty in that is that you just killed probably 16,770,000, some addresses because you're not going to be able to use them anywhere else. Remember our problem. We had this network where I just used temporary addressing and it's not going to be large enough for that network. Well, the flip side of that would be to go to something like 10.0.0.0 with a 255.0.0.0 subnet mask. That would mean Arizona could have 16 million some addresses inside of it, but that means that I can't use that anywhere else in this enterprise. So as I come to Nevada, I would have to use, let's just say 11.0.0.0, right? I kill another 16 million addresses. It wouldn't take us too long before we just flat out ran out of IP addresses. And now you're beginning to understand the world of classless addressing. Classless addressing doesn't mean that we throw out the original classes of addresses. Fact is, you can't. A 10 network is a Class A address. That's just how it was originally designed. But what you can do in the classless addressing world is change the subnet mask that you're applying to those networks. So if I had 10.1.50, I might, for example, go out and say, well, let's take 10.1.50.0 as my network, and I'll put a Class C subnet mask on it, like that. So now I've got one smaller network with 254 IP addresses on that little network, and now I can use, let's say, another network, 10.1.51.0, somewhere else, because that's now a different network. I have a different subnet mask. That's the world of classless addressing, and that's what the world that we live in. And by the way, I don't know if you know it. My finger's going crazy. We just did subnetting. That was it. This right here, if you want to know what is subnetting, that's it. Subnetting. You just did it right there. You just took a Class A address, which was originally in the original RFC specification that was written to design IP addressing. They said it should have this subnet mask, and you said, no. It doesn't work for me. That's too big of a subnet mask. I want to put a different subnet mask on it, and now you are a subnetter. You just did subnetting. Now, that's really easy subnetting. That's the I would say the very decimal-y version of subnetting, because we can get a lot more granular with the idea of subnets. But that's all the idea of subnetting is taking a large network and breaking it down into smaller sub-networks. Wait, hang on. Pause it. That's the idea of subnetting that just popped into your mind right there. That's where the word comes from, is breaking one network into smaller sub-networks. But it all starts with adhering to the original class of address. I cannot, at least if I want to have a good conscience about me and have a network that is compliant in any way to any kind of standard, I can't go backwards from the original design. As in, I'm not going to go in and say, well, 192.168.1 was originally a class C address, but I'm going to back up so it doesn't, like, I twitched even as I say that, because you can't do that. You can't go back beyond what the original standard is. Would it work? I don't even know. You just wouldn't, right? Subnetting is going further. It's taking those subnet masks and making them more specific, taking a larger network and breaking it down further. Hang on. So before I wrap this nugget up, I want to make sure you guys have the other values. I just told you that Class A address has 60,777,777, right? That many client devices. This guy, a Class B address, is again smaller than Class A, but still 65,534 usable IP addresses on there. And when I say usable, that's because you can't use the first and you can't use the last IP address of every single network. And you'll hear me say this multiple times. The first address identifies the network. It's like the name of the network. The last address is a broadcast address. If I want to send a broadcast to everybody on that network, I send it to the last IP address. Fact is, you just can't assign those two to a device. So the usable is always two less than the number of addresses that are in the network. So this guy is how many usable, this guy how many usable, this guy 254 usable. And now you see why you see this subnet mask all over the place. This page is just full of scribble now. This is what I would call lazy subnetting. And it's not a bad way. It's just simple. Or how about simple? Lazy implies like I'm judging you. Simple subnetting is just like, I don't have to really know that much about subnetting to do that. To put a Class C address on other things, and that's why you see that all over the place. Whew, that's enough. So we've got to put the lid on the jar because that's enough for you to digest right there. You now have seen the original 5 classes of IP addresses, of which 3 are the really important: Class A, Class B, Class C. I would make sure that you can recognize what IP address something is just by looking at that. As in, you should know at least Class A, B, C, probably D, the numeric values that are assigned to each one, and be able to pull that out of a hat in any given moment, because you'll often see that in network environments and have to recognize what that is. So you've seen the original classes of addresses. You've seen a classful design. You've seen that we live in a classless world, and you've seen simple subnetting. And now we're going to get a little bit more advanced. Whew, such good stuff. I hope this has been informative for you, and I'd like to thank you for viewing.